All right, this is 6.11 projectile motion. We're going to learn how to calculate motion in 2 dimensions. So we're going to start off with vocabulary words, which hopefully you already picked up with your outline. So the projectile is any objects shot through the air. The trajectory is the path that that object takes. The range is going to be the distance, so the x part, that the projectile travels. The flight time is going to be the amount of time that the object actually spends in the air. And here's some vocabulary words put together. The trajectory of projectile motion is a parabola. That means that when I chuck this duck, it is going to travel in a parabola path, like that. At the very top, the velocity in the y direction is going to be 0. It's the same as when we throw the duck up, right? At the very top part, it hesitates for just a second at 0. So it's going up. As it slows down as it goes up, it stops, and then it speeds up as it comes back down. So that is still the same. It just also has a y or an x velocity, which causes it to go to the side. So that is helpful when we're solving for, like, how much time does it take to reach the top, or what is its maximum height. Those things are very important there. We'll do them, don't worry. I have a couple of clicker questions in here just so we can get them in there. Are you guys ready for the clicker questions? That's what I thought. One. Are we ready? Here is the first clicker question. What is the range of a projectile? By the way, my clicker questions are kind of easy today. Waiting on 4 more people. One more person. Here we go. Okay, the range of a projectile is how far the projectile goes. So that means it's looking at its horizontal distance. Yay! Yay! Okay, question 2. Define the flight time of trajectory. We're missing 2 people. I think it's clicker 1 and 2. I'm not sure. There we go. Okay. So the flight time of trajectory is the total time the projectile was in the air. Answer C. Okay, projectile motion. Projectile motion is explaining, the movement in x and y. And the x direction is not affected by the y direction. And the y direction is not affected by the x direction. Just like with our forces are x and y. We have to split them up. So we have to do the same thing when we're talking about kinematics. This means that an object drops, and an object that is thrown horizontally, like my duck here, if I threw it off to the side of this table, like this, that means that they're going to land at the same time. And it's because they have the same force of gravity acting on it. One just has an x velocity, which causes it to be more to the side than the one that was just dropped. That x velocity doesn't have a force acting on it. There's no, we're going to ignore air resistance. There's no motor, there's no fan or anything on it, so it has no force in the x direction. So once it starts with this velocity, because of Newton's first law, inertia, it's going to stay with that same velocity in the x direction. All right, so here's some pictures. When you're throwing something off horizontally, like this is my duck. Again, horizontally means it only has velocity in the x direction when it starts, and then it reaches the end of the table. It keeps that same x velocity, but then it falls. So in the y direction, it falls. So it starts with 0 in the y, and it starts to accelerate down, 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 and as it accelerates, it gets faster. So accelerating. In the x direction, since there's no force, it continues with the exact same x velocity. That means that the faster that I chuck the duck across the table, the further out it's going to land, because it had that same amount of time, it has a longer amount of time, or a larger velocity in order to go faster and make it a larger distance. So here we have accelerated, there's a force, and here no force. So if we put that together, you can see that as it falls, the y velocity gets larger and larger and larger, and the x velocity remains exactly the same. Okay. And now we'll talk about something that's actually launched. So now if I take the duck and I launch it at some sort of angle, like this, it is going to have the up-down, like I chucked it up and down. So it starts with a large velocity, because just as it leaves my hand, it's going pretty fast. And the force of gravity is slowing it down, because it's pulling it down. So it slows all the way down until it reaches 0. And then as it falls, it starts to speed up faster and faster and faster. And you can see that these velocity vectors are perfectly matched because it's a parabola. In the x direction, because it's launched at some angle, it's going to be some x component of that velocity. There's no force in this direction, so there's no acceleration, which means that the velocity won't change. So it's going to continue with that x component the entire time. If we put these two things together, you end up with the parabola, where all your x components are exactly the same. And you can see your y components come from over here. First they slow down, get smaller, and then they start to speed up as they fall down. And that's because only gravity is pulling it down. For our problems, for this chapter, we are going to pretend like there's no air resistance, and there's no motors, or there's no anything else in the x direction. So the x direction should never have a force. Only the y direction has the force of gravity in it. It just simplifies our problems. Okay, are you guys ready for the next slide? Look pretty good. Okay. These are the steps for solving 2D motion. You're going to use this along with all the steps that we normally use up here on this poster. You're going to split the problem into the x and the y dimensions, just like we did for forces. You'll have an x side and a y side. Your vertical motion's acceleration is going to be negative 9.8. That's gravity. Most of the problems that you do, like 99% of the problems you'll do, will be on Earth, so we can just assume negative 9.8. The horizontal motion is going to be 0 meters per second in the acceleration because none of the problems that we are going to do are going to deal with air resistance or with motors or planes or anything. Now, the only thing that can cross the x and y axis is time, because time is not affected by the x or the y. It is completely independent. Hello? Mm-hmm. Yes. Mm-hmm. Okay. Okay. You're supposed to be in 9101 taking the second part of your test. All right, are we ready? Can I move on? You're supposed to say something, aren't you? Yes. Yeah. I was looking for the nose. I still see people writing. All right, here we go. So here's our practice, and I don't know, we have about half an hour left. We'll get through this one and maybe part of the next one. So the first thing that we're going to do, you want to make sure you have at least half a page to write on, just so you know. About a half page. And I'm still going to use some of these things mixed with the stuff that was on the last slide. So the first thing you want to do is read the problem. It says a stone is thrown horizontally at 10 meters per second off a building that's 50 meters high. That seems really short and easy, right? Like, not a problem. Okay, well, this is a very detailed problem. So just so you know, don't let it, be like, oh, it's going to be easy. There's only 2 numbers. Yeah. Okay, so the first one we're going to look at is how long does it take for the stone to hit the ground? So we will draw a picture, right? Draw a picture. Here is the building. It is 50 meters tall. Here's the ball that's thrown horizontally, so it should something like the last half of a parabola. And here's the ground. And it is shot with a 10 meters per second velocity that's horizontal. So there's my picture. You want to draw pictures for these because some of our numbers come from the picture. And I mean, eventually you can get to the point where you don't need the picture. But when you first start out, let's draw the pictures today. Okay, now, down the center of your page, I want you to draw a line straight down the center. Like this. And it really only has to go about half your page, but, that's where you're going to do all your calculations. And then we're going to draw X and Y and units. We're going to do this for 4 lines. Now, some people can get by without drawing the grid, and that's fine. It's just when you first start out, it's really hard to kind of figure out what your variables are. I mean, if you have equations and you know your variables, you just plug your variables into your equation, and that's math. But the physics part of this is trying to figure out what the variables are. So this kind of helps you organize your information, and that's why I teach you how to draw in a grid. Now, the grid isn't perfect. I did make it. Every year I make a little bit of a different change to it, but it does kind of help you figure out what you need. On the right here, it's going to be meters, meters, meters per second, and meters per second squared. And what I'm drawing here in this grid in blue, you're going to draw every single time you do a problem. And then I'll change colors when I go to the stuff that's just for this problem. All right. In the first part, we're going to go initial and final. Now, in my AP class, we actually call it R initial and R final because R means position, and position is made up of some X position and some Y position. But when I write R for the rest of my classes, they get confused. So we'll just call it initial position and final position by doing I and F. But if you ever see it and you ever take another physics class, R is what we use to talk about X and Y together. Okay, and then this one's going to be a velocity initial. So you have velocity initial in the X direction and velocity initial in the Y direction. And the last one's going to be acceleration. All right. Under the velocity, we're going to go cosine and sine. This is going to break your velocity into the X and the Y sides, just because it's a component, it's a vector, it needs to be broken into the two. Position isn't really a vector because it's just talking about like a spot, not really a direction. It's not talking about displacement here. And acceleration is going to be constant. So we already know that acceleration in the Y direction is going to be gravity. So that's something we can put in here, negative 9.8 under AY. And then in this X spot for acceleration to be 0 because it has no motors, no X force causing it to speed up or slow down in the X direction. It only has gravity effect.
And this is the stuff that's always going to be in the graph.
Pretty much it's going to look like this. The one other thing that we usually know is that our starting point is going to be 0. It's the X point. We usually make this 0. We don't usually start at like 5 ahead of it. So the stuff in blue here is something you're going to write pretty much every time. I can't think of a time that you wouldn't do this. Unless you were like on the moon, this would change. Or you were starting in the middle of the problem, like at halfway through the problem, then you could change that. But this will get you through the problems today, definitely, and probably for the rest of the chapter. Okay, now in these next spaces, we're going to put the equation. All of the kinematic equations will work here, especially the first 3 here. But I like the long equation because I usually use that in every single projectile equation motion problem. You can use the other two, the short A equals VF minus VI over T, or the VF squared equation. Those ones are very specific. So for instance, if you're looking for final velocity, which we will use them at the end of this problem. But to start off with, if you start with the long equation, you should be fine. So I'm going to say every time, start with the long equation. So on this side, we have to do all the y stuff. So this is y final equals 1/2 at squared plus VIT plus y initial. And on the x side, we're going to do the same equation, but with x instead. And that's going to be your setup for every problem. One more thing, on the side here, not under x or y, we're going to put time. Because time can cross from the x to y, so it's just kind of like on the side. Like, don't forget about time. So now we have to go about solving this problem. This problem is a ball being thrown horizontally off a cliff. So I've drawn that picture here, and I need to write a coordinate system over top of the picture so that I can kind of fit it with my grid. There's two options. You could start the coordinate system at the ball, or you can start it at the ground. I like to start it at the ground because then I kind of eliminate some of my negative numbers. So I'm going to go, my y-axis is here, my x-axis is here. So this point right here will be 0, 0. So if this is where I start my initial point, and this is where I end my final point, what would the initial coordinate point be? X, y. According to the grid.
C. 0.50.
0.50, good. And what would this point final be? It'll be something. We don't know what that something is, 0. And that's unknown. We don't know. Because we're not sure. We haven't done the math yet to figure that out. So it's just a space for right. So we could take this initial point, this 0.50, and put it under our initial in the grid. So 0, which we've already written, and 50. And our final point, we have a blank, which we don't know. I'm going to call it XF because it falls under X and F. This will be XF. And then, comma, 0. So we've filled out a lot of the grid already. And I find that that's where the people struggle the most. They don't know what to put in an X, Y for the initial and final. If you draw the picture, it'll really help you out. You just put the coordinate system right on top of it and tell you what your coordinate points say. Yes?
At the very top of the coordinate system, next to B, what is that?
That's an I. I got a little crazy with the I. I'm sorry. There you go. There you go. Okay, ready for the next part? Of course you are. All right, the next part is we're going to look at the velocity. The velocity is 10 meters per second shot horizontally. So what angle is it shot at? 0. So this 10 meters per second at 0 degrees is going to be 10 cosine 0 and 10 sine 0. So we're taking care of vectors right in the grid. Any questions about that? We can simplify that in our calculator real quick. You can do 10 sine 0 and 10 cosine 0 in your calculator, and you're going to find that 10 sine 0 actually goes to 0, which is pretty nice, and 10 cosine 0 actually goes to 10, which is also fairly nice. Now, if it's shot at any sort of angle, it won't be that nice. But anything that's shot horizontally is only going to have the x component and no y component. All right, what do you think we do next? Plug it in on the x or the y side. All right. If you look here, on the y side, we have all the numbers. And on the x side, we're missing a number. And we're also missing time. So the best way to solve would start with the y side. Now, if you decided to start with the x side, you're going to get to some point where you have two variables and you can't simplify anymore. That's fine. You can come back to that. Just move to the y side, solve as far as you can, and sometimes you'll end up with two equations and two variables. You can plug those in with substitution or elimination. So if you get stuck, just try the other side. And that will help you get unstuck. But I almost always start with the y side because we know gravity. And that really helps us. Okay, so plug this stuff in, cover up the x side. You don't want to see the x side. You're only using the y values. So y final is going to be 0. 1/2 a in the y direction is negative 9.8. We don't know t. Plus v initial, which is 0. We still don't know t. Plus y initial, which was 50. So we found our variables. That's the physics part. We drew the picture with the coordinate system. That's the physics part. We plugged our variables in. Now it's just algebra. So you should be able to get, once you get to this part, should be pretty easy. Okay, so let's solve. We have 0 equals negative 4.9 t squared plus 50. I'm going to move this 4.9 t squared to the other side. 4.9 t squared equals 50. Divided by 4.9 gives me 10.2. So t squared equals 10.2. We'll square root both sides. And that gives me 3.19. Make sure you put that unit in. And that answers part A. So I can actually add that up here if I wanted to, 3.19. All right, it is 10:15. If you have BCC, don't forget that you need PG. So the next step is going to go to the x side. Now we have time, and time can cross to the x side. So we should have enough stuff to solve for this xf. So let's plug this stuff in. We don't know what xf is. Remember, you're only using stuff from the x side, so cover up that y side. This will be 1/2. A in the x direction is 0. We know t now is 3.19. VI is going to be 10 times 3.19 plus XI, which was 0. Now these zeros in there make our equation very simple, because we're going to take this out because it's multiplied by 0, and this is 0 over here. So basically we're left with 10 times 3.19, which will give us 31.9 meters. So that solves for B. How far did it go? Any questions on that so far? We still have to answer C and D, which is talking about the final velocity. It says, what's the horizontal and vertical component just before it hits the ground? We never talk about it like as it hits the ground or after it hits the ground, because we're applying forces. That's more like impulse and momentum stuff. But we're always talking about, like, what does it hit the ground with, like right before it goes to 0? Because we know when it's on the ground, velocity is going to be 0, unless it's sliding. But that's just applying a lot more forces. We just want to know, like, right before it's touching the ground, what's its velocity. So when we find V final, that's what we're talking about. So C and D talk about V final. The problem with the grid here is that we don't have a V final anywhere in it. So we need to look at the equations with V final in it, which are either VF squared or the A equation. I like the A equation because it's very short, and I'm a little lazy. So I'm going to do the A equation, and you can extend your paper down. I'm actually running out of room here, so I'm going to pretend like my paper is extended over on this side. So this is just like lower on my paper. I'm going to write the A equation for both of these. So it'll be A V final minus V initial over T. This is, remember, the X side still, and this is the Y side. And this one's going to be A V final minus V initial over T. So these equations I'm going to use to plug in my stuff. So A in the X direction is still 0. I'm looking for V final. My V initial was, in the X direction, 10, and my time was 3.19. Which, basically, you're going to end up with V final is 10. Does that make sense? If it starts in the X direction, it starts at 10 and it ends at 10 in the X direction. Why is that? There's no force in the X direction. So there's nothing there to change it. So it has to remain the same. So you could just kind of skip that equation and be like, there's no force. It's going to have the same X component. So that's something that you can kind of skip if you want. Okay, in the Y direction, let's add this stuff. We have, in the AY, we have negative 9.8 We're looking for VF minus V initial, which was 0, and time, which is 3.19. This gives us 31.3. Does this make sense? Negative 31.3?
It's going down.
Yeah, it makes sense. It's going down. It has to have a negative velocity. It'd be weird if it was going up. We threw it out the window and it started going up. That would be weird. Okay, so this is your X stuff, don't forget. So this is I hat. And this is the Y stuff, so this is J hat. So now what you're going to do is you're going to do the velocity stuff, or the vector stuff. We're almost there. This is C right here. This part is C.
And now D is what's left.
And now D is what's the magnitude and direction. So that's back to our vector stuff. So magnitude and direction of velocity final is going to be the square root of x squared plus y squared. Now you can ignore the negative for this one because it's going to disappear anyways when you do it. Make sure you put all those parentheses in there if you do include the negative, because you want to make sure your calculator does it right. We have an x component and a y component, and we're trying to put it back into vector form. So we have to use our vectors. And I got 32.9. So there's the magnitude in part B. And now I have to do direction. Tangent inverse of y over x. Now it has a negative y value and a positive x value. So we need to add 360, our little adjuster, to make sure it goes in the right coordinate system. And I got 288. Now, does 288 seem like a good answer?
Yes.
I mean, that would kind of mean that it's this direction, right? 288. So, yeah, that seems about right. So when you're getting your answers, just make sure they seem to make sense. Because the more that you kind of do that, the easier the conceptual questions will be on the test. Because I know there's lots of conceptual questions. So that's how the EOCs can be. Okay, we have about 5 minutes left. Tomorrow we're going to go over projectile motion with angles. And so instead of it being shot horizontally, it's going to be shot up a little bit.